Welcome to Part 6 of this week's online lecture. In Part 6 we will continue our discussion of rigid diatomic molecules and in particular look at the source of degeneracy. I want to briefly summarise some of the important points from earlier in the lecture before continuing our discussion of diatomic molecules. First, I want to appreciate how we come up with the energies for the quantum states. No matter which spectroscopy we discuss, the process will be the same. We will be solving the Schrodinger equation. The first thing we will do is identify the Hamiltonian. This is determined by the system. For the rotational system, there is the rotational kinetic energy operator, and that's it. The potential energy is zero, just like the particle in the box. With the Hamiltonian identified, we simply solve the Schrodinger equation. The solutions are all well known in mathematics, so this is just a matter of looking up the general solutions. With the general solutions, we apply the boundary conditions particular to the problem, and this results in quantization. We can then operate on the wave function with the Hamiltonian to identify the energies as a function of the quantum number. How did this all work out for our rotational system? Well, we looked at the simplest of molecules, that is the diatomic. We also assumed that the bond was rigid, so we had what was known as a rigid rotor. We will relax this approximation later in this topic. When we solve the Schrodinger equation, then this is the solution of the energies of the rotational levels. It is equal to the rotational constant B times J into J plus 1. So when J is equal to 0, the energy is equal to 0. If J is equal to 1, it is equal to 2B, and if J is equal to 2, it's equal to 6B. And this symbol F is the rotational energy term. This is the energy expressed in wave numbers. So the rotational constant B here is also in terms of wave numbers. In spectroscopy, we have light interacting with matter. In order to interact, the incoming photon energy, h nu, must match the energy difference between two rotational states. Well, the energy difference between J equals 1 and J equals 0 is 2B minus 0 is equal to 2B. And the energy difference between J equals 2 and J equals 1 is 6B minus 2B is equal to 4B. And the energy difference between J equals 3 and J equals 2 is 12B minus 6B is equal to 6B. Rotational energy is quantized. This quantization came about because of the boundary condition that the wave function must be single-valued as our reduced mass particles circumvented the origin and returned to its original position. And so that's why the energies of our system are indeed quantized and we get our J quantum number. The other thing we can do with quantum mechanics is determine the selection rules. This is because the selection rules come from the transition moment, and the transition moment depends on the wave functions of the system. So for the rotational system, there is the gross selection rule, which is that our system must have a permanent dipole moment. Mu is the symbol for the dipole moment. If the molecule has a microwave spectrum, then it must be non-zero. In terms of group theory, molecules which possess a central inversion is a sufficient condition for the molecule to not have a dipole moment and therefore be microwave inactive. The second selection rule, which again comes from consideration of the transition moment, is that delta J is equal to plus or minus 1. Delta J is the change in rotational quantum number during the transition. That is the final rotational quantum number minus the initial rotational quantum number. The selection rule requires that this can only change by 1. So I can go from J equals 2 to J equals 3, and I can go from J equals 3 to J equals 4, but I cannot go from J equals 2 to J equals 4. Remember that we did manage to justify this semi-classically by conserving angular momentum in our photoreaction, and noting that the photon has 1 unit of angular momentum. The angular momentum of a photon can be plus or minus 1. So therefore, if I am going to conserve angular momentum, the amount of angular momentum I have in the reactants, that is, the angular momentum of the J state of the molecule plus the angular momentum of the photon, must be the same as the angular momentum of the system after the photon has been absorbed. And so the angular momentum can either go up to J plus 1 or go down to J minus 1. It cannot stay at the same J level, and it cannot go up to the J plus 2 level, where J is the initial quantum number. So this is the picture we end up with, and these transitions in red, where J changes by plus 1, are all allowed, and these transitions which I have crossed out, where J is changing by 2 or 3 respectively, are not allowed. This leads to our spectrum. The transition from J equals 0 to J equals 1 will occur when the system absorbs a photon of 2b. Associated with this is the spectral line at 2b. The transition from J equals 1 to J equals 2 happens when the system absorbs a photon with energy 4b. Associated with this will be a spectral line at 4b. The next transition from J equals 2 to J equals 3 will lead to a line at 6b. Each of these spectral lines are separated by 2b. And this explains the equidistant separation of lines in a rotational spectrum. So what is the use of doing this? Well, I have a model which expresses the energy of each of the spectral lines in terms of rotational constant. Once I've got the rotational constant, which I can get by simply dividing the frequency difference by 2, I can calculate the moment of inertia. Because the rotational constant is inversely proportional to the moment of inertia, and once I've got the moment of inertia, I can use that to determine the bond length of my molecule if I know what the reduced mass is. Or perhaps, if I've got a spectrum of more than one isotope, I can determine the isotopic abundances of the various elements. I've already mentioned degeneracy earlier in this module, and I've mentioned that it is going to be important. And in particular, I've mentioned that the degeneracy will be important in terms of the intensity of each of the spectral lines. Remember that the intensity is dependent on the Boltzmann distribution. And the Boltzmann distribution, of course, depends on the energy gap, but it also depends on the degeneracy of the energy levels. So we need to work out what the degeneracy is for each of our levels. So let's go back to the solution of the Schrodinger equation for my rotational system. This was the result of solving the Schrodinger equation. The energy of a rotational level J is equal to J into J plus 1 times h bar squared all over 2I. We can relate our rotational energy, E sub J, to my angular momentum, which I've given as J. It is a bold J because it is a vector. And I can write down my rotational energy simply as the angular momentum squared divided by 2I. This is analogous to linear kinetic energy being equal to the linear momentum squared divided by 2m. Remember that angular momentum is the moment of inertia times the angular velocity. So the angular momentum squared would be I squared times omega squared. And if I divide through by 2I, it will be equal to a half I omega squared. So we can more easily appreciate the analogy between a half I omega squared for rotational kinetic energy and a half mv squared for linear kinetic energy. Angular velocity is the analogue of linear velocity, and the moment of inertia is the analogue of mass. Now that I know my energy is equal to J squared over 2I, I can compare this to see that J, my angular momentum, is equal to the square root of J into J plus 1, all times h bar. So this is the magnitude of my vector. but it also has direction. So in this particular case, it is telling me, as it is pointed upwards, that my molecule is rotating in an anti-clockwise direction. So if you know where the vector is pointing, you can use the right-hand rule where the thumb points in the direction of the vector. Then the fingers determine the direction in which my molecule is rotating. If the vector is pointing downwards, then my fingers point in a clockwise direction, which means my molecule is rotating in a clockwise direction. So there are two directions in this particular case. With reference from the axis of rotation, it could be rotating clockwise or anti-clockwise, just depending on whether my angular momentum is pointing upwards or downwards along the axis of rotation. I need to discuss the orientation of the angular momentum vector in space. So far, quantum mechanics has told me the magnitude of the vector, but I want to know the direction. Say I've got the z-axis that can be defined however you want. It's an arbitrary axis. I'm going to project my angular momentum vector on this arbitrary axis in order to tell me something about the orientation of the rotational motion. So I'm going to project my vector onto my reference axis z. So if this is my z-axis or laboratory axis in blue, and this is my rotational axis in red, and here is my angular momentum vector, I just project the angular momentum vector onto the laboratory fixed axis. This projection makes a right angle with the laboratory fixed axis. So you can see I've created a right angle triangle where the j vector is the hypotenuse and the projection of the vector will have a magnitude jz. Depending on how the molecule is oriented, the value of jz can vary anywhere from the actual magnitude of the angular momentum in the positive direction to the magnitude in the negative direction if I rotate it all the way around. But that is not going to be the case. In fact, it isn't arbitrary. My molecule can orientate itself with respect to my laboratory axis, but only in certain directions. The orientation is also quantized. This is a bit tricky to appreciate. My value of jz here can only vary from plus j to minus j. So what that tells me is that my vector can never be perfectly aligned along the z-axis because the magnitude of my j vector is the square root of j into j plus 1, all times h bar. And my jz can only have an absolute magnitude of j times h bar, whereas j can have a magnitude of the square root of j into j plus 1, all times h bar. So it is always slightly larger. But the value of jz is quantized. Notice how many possible orientations there are for a particular value of j. For instance, if I'm in the j equals 2 rotational level, then there are only 5 spatial orientations that my molecule can be in. It can be in mj is equal to 2, mj is equal to 1, mj is equal to 0, mj is equal to minus 1, and mj is equal to minus 2. If I'm in the j equals 1 level, there are only 3 possible spatial orientations. If j is equal to 3, there are 7 possible spatial orientations. And if j is equal to 4, there are 9 possible spatial orientations. You can probably think of an analogue you've already come across. How many s orbitals do you have in a particular state? You have 1. How many p orbitals do you have? 3. How many d orbitals do you have? 5. How many f orbitals do you have? 7. And it is for exactly the same reason. Remember, you've got your L quantum number, which for s is 0, for p is 1, and for d is 2. And you have your ml quantum number, which can only have integer values from L to minus L. The maths underpinning this is identical to that for rotational motion. This mj quantum number is also quantized because of a boundary condition that must be satisfied, and it is exactly the same type of boundary condition that leads to the ML quantum numbers in atomic orbitals. The reason why we've got two quantum numbers in this problem, that is the J quantum number and the MJ quantum number, is that in order to define the position of a particle on a sphere, which is the model that we're using, we need two coordinates, theta and phi, latitude and longitude. There is a boundary condition associated with both of these coordinates, and so there is a quantum number associated with each of these boundary conditions. You always have the same number of quantum numbers as you have coordinates, because there is a boundary condition to be satisfied with each coordinate. So when we look at vibrations and electronic spectra, we will see how that gets more and more complicated. So we've come up with this idea of a spatial orientation before. We've already met them with atomic orbitals. You can also appreciate that p orbitals, for the hydrogen atom at least, have exactly the same energy. You can see that it doesn't matter which p orbital the electron is in, it has the same energy because they are identical to one another. It starts to get a little more complicated to appreciate that the d orbitals are all identical to each other. For the p orbital, you can see it's just a matter of rotation, but for the others it is not so obvious. The dz squared orbital doesn't look particularly like a dxy orbital, for instance, and yet you know that they have the same energy if we have a single electron system. The reason you can't tell that they have the same energy is because you are a three-dimensional being. If you were a five-dimensional being, they'd look identical to one another. But that is, I admit, a little abstract. This issue of spatial degeneracy does take some getting used to. On this slide, you can see two representations of this spatial degeneracy. On the left, you can see the J vector being projected onto the z-axis. When j is equal to 2, there are 5 possible mj values from +2 to -2. On the right, you can see 5 cones being swept out to represent the angular momentum vector. These cones are meant to remind you that the angular momentum vector can lie anywhere on the surface of one of these cones for a particular value of mj. You don't know where on the cone, as you only know the projection onto the z-axis. It does make sense that the rotational energy depends on j, that is, the rotational quantum number, but doesn't depend on mj. It should not matter what the orientation of the rotational axis is with respect to the laboratory. There is nothing about space which makes a particular direction more important than another, or with regard to rotation, easier to rotate around than any other. The importance of this spatial orientation is that it leads to degeneracy. If my molecule is in the J quantum state, then there are 2J plus 1 possible orientations which all have the same rotational energy. This is the definition of degeneracy. Let's look at this degeneracy in more detail. Because the molecule can be in these 5 different orientations when in the J quantum state, it means that we have 5 energy levels, and all those 5 energy levels have the same energy, so they are all degenerate. So this is where degeneracy is coming from. Although this quantization of spatial orientation has not changed the energy of the system, it is still a separate energy level. So my J equals 0 level is not degenerate, as the only possible value of mj is 0. My J equals 1 level is threefold degenerate. There are 3 energy levels with exactly the same energy, which refer to the mj equals 1, 0 and -1. My J equals 2 will have 5 energy levels of the same energy. My J equals 3 level will have 7 energy levels, and so on. So the number of energy levels with the same energy is increasing, and you can work it out. The number of degenerate energy levels for any value of J is equal to 2J plus 1. Here are my energy levels again. but I know that in fact the degeneracy, given the symbol G for j equals 0, is j sub 0 is equal to 1. When j is equal to 1, mj can equal 1, 0 or minus 1, and so the degeneracy of this level, G1, is equal to 3. When j is equal to 2, there are 5 levels. When j is equal to 3, there are 7 levels, and so on. In general, the degeneracy of the jth state, G sub j, is equal to 2j plus 1. So let's reinforce that again and summarise what I've tried to illustrate so far. My rotational energy, E sub j, is quantized because of boundary conditions for a particle moving on a sphere. If we solve the Schrodinger equation, we'll come up with this formula, and the boundary conditions means that it is quantized, so that j can only have values of 0, 1, 2, 3, etc. The angular momentum we can determine to be j is equal to square root of j into j plus 1, all times h bar. And again, it is quantized. It depends on its j quantum number. But the component of j on an arbitrary axis, that is jz, is also quantized. This is the spatial quantization arising from a boundary condition on the second coordinate for my particle moving on a sphere. And so jz is equal to mj times h bar, where mj is my new quantum number. And mj can have values of 0, plus or minus 1, plus or minus 2, all the way up to plus or minus j. It is limited by which rotational level that you're in. And that leads to my degeneracy of 2j plus 1. Surprising though it may seem, my rotating body cannot point in any arbitrary direction. Its orientation is determined by quantum mechanics. If I set myself rotating, I can rotate apparently in any direction because my rotational quantum number is huge. The difference in rotational energy level to the next is minute. You cannot feel the discontinuity. Similarly, you cannot feel the quantization in spatial orientation because the difference in angle is minute. You can't see quantization by looking at macroscopic objects. You can only see this at the quantum level, which is the reason why it appears so weird, because we never really appreciate it. This is the end of part 6 of this week's online lecture. Please continue on to part 7.